The ground underneath Chicago is sinking. Not in the way a beach erodes or a cliff crumbles into the sea. There is no hole opening up, no dramatic collapse you could film. It is quieter and stranger than that. The entire surface of the city, and the cities around it, Detroit, Columbus, Indianapolis, is settling downward, steadily, year after year. And it has been measured now to the millimeter by satellites looking down from space. And when scientists finished mapping exactly how much the American Midwest is dropping, and turned to the question of why, the answer came back in two parts. The second part is one we caused ourselves, and we will get to it. But the first part is so strange that when you first hear it, it sounds like something a person made up. The Midwest is being pulled downward by an ice sheet. An ice sheet that finished melting more than 10,000 years ago. An ice sheet that no living thing has ever seen, that vanished before the first cities, before writing, before agriculture, and yet is still today reaching up through the rock and dragging the ground down a few millimeters every year. That is the detail that tells the real story. And before we get to it, there is one honest thing that has to be said. Because it changes how you should hear this entire video. This is slow. We are talking about millimeters a year. Nobody is going to fall into a chasm. The ground is not going to swallow Chicago next Tuesday. And here is the part that is genuinely counterintuitive. That slowness is not the reassurance it sounds like. The slowness is exactly what makes it dangerous. For a reason that has nothing to do with how fast the ground drops, and everything to do with the fact that it does not drop evenly. Hold that thought. It is the whole point, and we will build to it. First, how do you even measure something like this? How do you know a city is sinking 2 millimeters a year when 2 millimeters is thinner than a stack of 2 credit cards? The answer is a technology called INSAR, radar interferometry, and it works from orbit. Satellites fire radar pulses at the ground and measure with extraordinary precision how long they take to bounce back. By comparing those measurements over months and years, scientists can detect changes in the height of the ground surface, smaller than a centimeter, across an entire city, block by block. One of the researchers behind this work, Manucher Shirzei, an associate professor at Virginia Tech's Earth Observation and Innovation Lab, describes it as getting a CAT scan of the Earth's surface, except from space. In May of 2025, Shirzei's team, led by a scientist named Leonard O'Henhen, published a study in the journal Nature Cities that did exactly this for the 28 most populous cities in the United States. Places that together are home to around 34 million people, roughly 1 in 8 Americans. And the headline finding was stark. Every single one of those 28 cities is sinking, at least in part. In 25 of them, at least 65% of the urban area is losing elevation, and the Midwest is right in the middle of it. Chicago, Columbus, Detroit, Indianapolis, all of them among the cities where the sinking is most widespread, covering, in some cases, close to the entire footprint of the city. Chicago as a whole is dropping at a little over 2 millimeters a year, and in at least a tenth of the city, the rate is faster than 3 millimeters a year. 2 to 3 millimeters a year does not sound like much. Over a decade, it is a couple of centimeters. Over the lifetime of a bridge or a building or a water main, it becomes something that matters a great deal. But to understand why it is happening, we have to go back, way back, to the ice. Around 20,000 years ago, at the peak of the last ice age, a colossal mass of ice called the Laurentide Ice Sheet sat on top of North America. It is hard to overstate how big this thing was. At its maximum, it was larger than the entire ice sheet that covers Antarctica today. It buried all of Canada. It reached down over the northern United States, over the Great Lakes, over the upper Midwest. And it was not a thin skin of ice. It was more than a mile thick across enormous areas, and thicker still toward its center. A dome of ice pressing down on the continent with a weight that is difficult to put into human terms. Now, here is the thing most people never learn about ice sheets, and it is the key to everything. The Earth's crust is not a rigid, unmoving floor. Over long enough timescales, it behaves almost like a very stiff fluid, floating on the hotter, softer rock of the mantle beneath it. And when you put an unimaginable weight on top of it, it does what any surface floating on something soft does. It sinks under the load. Picture pressing your hand down into the middle of a firm mattress. Directly under your palm, the surface sinks. But watch the edges. Right around the rim of the depression you are making, the mattress bulges upward, pushed up by the material squeezed out from underneath your hand. That is not a metaphor for what the ice did. That is literally what the ice did to the crust of the continent. Under the enormous weight of the Laurentide Ice Sheet, the crust beneath the ice was pushed down, deep, into the mantle. And the rock displaced from underneath had to go somewhere, so it flowed outward and pushed up a great raised ring around the edge of the ice. Geologists call it the Forebulge, or the peripheral bulge. It is the risen rim around the depression, and it stood outboard of the ice margin, in a band running across the mid-latitudes of the continent. And that is precisely where the Midwest and the Great Lakes sit. On the Forebulge, on the raised rim that the ice pushed up, for tens of thousands of years, as long as the ice sat there, that arrangement held. The center pushed down, the rim bulged up, in a slow, stable balance. And then the climate warmed, and the ice began to melt, and the entire process started to run in reverse. When you lift your hand off the mattress, the depression under your palm springs back up, and the bulge around the edge sinks back down. The Earth does the same thing, just far more slowly, because the mantle rock it has to move is so stiff that it takes not seconds, but thousands upon thousands of years. The land that was crushed down beneath the thickest ice around Hudson Bay in Canada is now rebounding upward. It is still rising today, 10,000 years after the ice left, lifting measurably every year. And the Forebulge, the raised rim, is doing the opposite. It is collapsing, deflating, slowly settling back down toward where it was before the ice ever arrived. This is called, plainly, Forebulge collapse, and according to the National Oceanic and Atmospheric Administration's National Geodetic Survey, it is one of the single largest causes of natural ground movement in the United States. The agency puts it bluntly, regions on the old Forebulge have been sinking for thousands of years, and will keep sinking for thousands more. The Midwest is not sinking because of something that is happening. It is sinking because of something that stopped happening 10,000 years ago. It is riding the slow deflation of a bulge that an ice sheet raised. And the ground is still relaxing back down from a weight that lifted before human history began. If you want proof this is not just a model on a computer, it is written into the land itself. In 2020, a group of scientists studying the upper Midwest confirmed the ongoing collapse of the Laurentide Forebulge with GPS measurements across the region. And even more remarkably, a separate study found the ghost of the bulge preserved in the bedrock beneath the Mississippi River. The buried valley floor of the upper Mississippi holds a trench more than 100 meters deep and 300 kilometers long, which the researchers interpret as a partial cast of the ancient Forebulge, carved and buried as the great river cut across the rising and falling land. The river itself is a recording of the ice. The Forebulge collapse across these areas runs at roughly 1 to a few millimeters a year, which is slow and permanent, and completely beyond anything human beings can stop. But the ancient ice is only half the answer. Because if Forebulge collapse were the whole story, the sinking would be gentle and gradual and roughly even across the region. It is not even. In the cities, it is faster and messier than the ice alone can explain, and that points to the second cause, the one that is us. When the Nature Cities team looked at what was driving the sinking in America's cities, they found that the ancient geology was real, but it was not the biggest factor. Around 80% of the subsidence they measured was associated with a single human activity: pumping groundwater out of the ground. To understand why that makes the ground sink, you have to let go of a common mental picture. An aquifer is not an underground lake. An open cavern full of water you can drain like a bathtub. An aquifer is rock and sediment, sand and gravel and fine-grained clay, with water filling the tiny spaces between the grains. And that water is doing structural work. The pressure of the water in the pore spaces helps hold the grains apart, helps hold the whole sediment framework open, the way air pressure holds up a bounce house. Now pump the water out faster than rain, and rivers can refill it. As the water level drops, the pressure in those pore spaces falls, and the fine-grained sediments, no longer held apart by water pressure, begin to compact under the weight of everything above them. The grains pack together, the pore spaces close. And here is the cruel part, the part Susanna Worth, a geoscientist on the study, emphasizes. In fine-grained layers like clay, that compaction is largely permanent. It is not a sponge that springs back when you add water again. Once those spaces collapse, they mostly stay collapsed. The ground has dropped, and it will not come back up. Chicago is a case study in this. According to the U.S. Geological Survey, long-term pumping has lowered the groundwater level beneath the Chicago region by as much as 900 feet since 1864. 900 feet. And as the water goes down, over the decades, the land above it slowly follows. So the Midwest has two forces pushing it down at once. Underneath everything, the ancient, unstoppable, ice-driven collapse of the Forebulge, a millimeter or two a year, forever. And on top of that, in the cities, the faster, human-driven compaction of aquifers being drained of the water that held them open. The ghost of the ice and the thirst of the cities, working the same direction. Which brings us, finally, back to the thing I asked you to hold at the very start. Why slowness is the danger and not the comfort. Here is the intuition that fools people. If the whole Midwest were sinking uniformly, all of it, evenly, at exactly 2 millimeters a year, like a single enormous elevator descending in perfect level, you would genuinely be fine. You would barely be able to tell it was happening. Every road, every building, every pipe, every rail line would go down together, keeping the same relationship to everything around it. Nothing would break, because nothing would be stressed relative to anything else. But the ground does not sink like an elevator. It sinks like a warped floorboard. Because the two causes are patchy. The Forebulge collapse varies from place to place. The groundwater compaction depends entirely on where the aquifers are, where the clay layers sit, where the pumping is heaviest. So one part of a city sinks at one rate, and the next part sinks at another. And the difference between them, the unevenness, is where the damage lives. Scientists call it differential settlement, and it is the actual hazard hiding inside these gentle-sounding numbers. Think about what that does to the things we build. Imagine a bridge with one end anchored in stable bedrock and the other end resting on ground that is compacting a few millimeters a year. Over a decade, over two, that far end drifts downward while the near end holds, and the whole structure is slowly, invisibly racked with stress it was never designed to carry. Imagine a building where one corner sits over a drain. Compacting aquifer and the opposite corner does not. The building does not sink. It tilts by a hair, and then a hair more, until the frame is fighting itself. Imagine a water main or a gas line running straight through a boundary where the sinking rate changes, being bent year after year at a single point. This is what Shirzai means when he calls it a latent risk. His warning is precise and unsettling. Infrastructure can be silently compromised over time, with the damage becoming evident only when it is severe, or potentially catastrophic. Not sudden, not visible. Just an accumulating, hidden strain in the bones of a city, in the bridges and the buildings and the dams and the buried pipes, that no one sees until something that should have held doesn't. And it starts small enough to be mistaken for nothing. Picture a homeowner in a Midwestern suburb, some ordinary morning, noticing that a door in the house has started to stick. It won't quite latch anymore. A few weeks later, a hairline crack appears, tracking up from the corner of a window frame. The floor in one room feels, if you really pay attention, very slightly not level. Every one of those is on the list of telltale signs the researchers name for early ground settlement. Cracks around doors and windows and foundations. Floors that slope. Doors and windows that no longer close square. And the homeowner will almost certainly blame the house. An old foundation. Settling, in the ordinary sense. They will have no reason to imagine that their entire neighborhood is a few millimeters lower than it was. That the ground beneath the whole street is riding the collapse of a bulge, raised by a wall of ice their 1,000 times great-grandparents never lived to see, accelerated by a century and a half of water pumped out from underneath them. Multiply that one house by a city. By the roads and the rail lines and the aging water systems that 34 million people depend on. As Leonard O'Henhen put it, a lot of small changes build up over time, magnifying the weak spots in urban systems. And it compounds with water in a second way. Because ground that has sunk sits lower against rivers and rising lakes, so the same drop that stresses a foundation also deepens a flood. For a lakeside city like Chicago, sinking land and the rising water of the Great Lakes lean on each other, and low ground floods first. So is there any good news in this? There is, actually, and it is real. And it comes from the difference between the two causes. The ancient half, the Forebulge collapse, we cannot touch. It is the relaxation of a continent, and it will go on for thousands of years no matter what anyone does. But the modern half, the 80% driven by groundwater, is human-caused, and that means it is human-solvable. If you stop over-pumping, and better still, if you deliberately put water back into the aquifers, a practice called managed aquifer recharge, you can slow the compaction. And in some places arrest it. Scherzier is direct that subsidence is a solvable problem, precisely because so much of it is our own doing. But he adds a caution that lingers. The payoff from recharging an aquifer, he points out, arrives on a timescale of centuries, even 1,000 years. And policy, especially in a democracy, tends to be made from one election to the next. So the remedy exists, and it works, and it asks us to act now for a benefit that lands 10 centuries from now, on behalf of people we will never meet. That is a hard thing to ask of any government, and it is the real reason the ground keeps sinking, even though we know how to slow it. So picture the last image. Somewhere in the upper Midwest, bolted to a concrete pillar sunk into the earth. There is a GPS monitoring station, a small gray instrument quietly listening to satellites, and what it is recording, right now, tonight, is the ground beneath it dropping. A millimeter or two this year. The same as last year, the same as it has every year for 100 centuries. The ice that started it has been gone for 10,000 years. Not a trace of it remains on the surface. No glacier, no cold, nothing a person would ever notice. But the ground remembers it. The rock is still relaxing back down from a weight that lifted before the first city was ever built. And beneath the streets, the water table keeps dropping, and the ground keeps following it down, in increments too small to see and too steady to stop. Tilting the world we built by a fraction of